welcome everyone. Today's presentation is going to be me teaching you a Query DSL with a little help from SQL. So I assume most of you have some sort of experience with Query DSL already. So I will just ask you if you have experience with SQL as well. That's good. That's a good starting point. So let me introduce myself first. So I am a founding engineer at Quesma. Essentially, we are building a database gateway solution. We are based in Warsaw, Poland. We're pretty fresh startup. We started our development in January this year. So 10 months, we are building our product with just 6 engineers at this point. I'll talk about product later on, but yeah, my previous experience prior to Quesma, I've been working at Elastic, where I have been building the cloud offering for over 6 years, and before that, I have been working at Boston area startup, which turned out to be a way bigger company after a few years, which delivered a crowd testing platform known as UTest, but the company name was Applause. And yeah, I did a lot of things over the course of like my 15 years in the industry, but primarily with around the backend software engineering. So, so why I actually decided to make this presentation? Well, first of all, let's have a little chat about the Query DSL. So Query DSL is actually one of its kind. It's exclusive to OpenSearch and Elasticsearch, and it didn't get any further adoption to any different database engine. Unlike the SQL, unlike GraphQL, it's not used anywhere else, which is quite surprising these days, because if we think about contemporary database solutions, they mostly tend to use like Postgres wire protocol, not to re-implement stuff from scratch, or like GraphQL adapters. So Query DSL, for some reason, is unique to those two products, and it has some sort of learning curve to it. It's not that steep, but yet it still exists, especially with more complex queries. Valid, like proper query, doesn't necessarily mean that we will get valid results, or at least the results that we are expecting to be. And one thing about my experience when querying huge Elasticsearch clusters back then when I worked at Elastic was that I tend to think of it as a write-only language, because whenever I wrote a query, I kind of executed it, looked at the results, and then coming back to the query after like a few weeks or months even, and having to write a query again, I was super lost and have to like refresh my memory again. And as it turns out, the large language models are super helpful with that. And there's lots of people who actually do not understand Query DSL, because it's way simpler to just type in to ChatGPT and it will pop out a result. Problem becomes when ChatGPT doesn't understand your point, then guiding it towards your solution might be a little tricky. So it's very good to have some sort of framework on how we are actually going to build, so sort of like a basic layout of a query in our head, so that we can build our queries with a lot of understanding and like know what's being done. And why I will be using the help of the SQL? Well, first of all, there's this phenomenon called the cross-linguistic transfer, where it applies to human-like languages. Like, I don't know, if you're, for instance, learning Italian and Spanish at once, you're most likely via spotting some correlations, learn much faster. Of course, there's flip side of it. So there are some pairs of languages that actually goes kind of against the learning boosting the learning process. So we will see how it works with SQL and Query DSL. I'm not sure why it's the first time I'm delivering this presentation, so I'm not sure what the results will be, but let's check it out. And the second thing is that actually this is one of the things that we are building right now at Quesma. So what we are building is a database gateway that you can put in front of your databases, such as OpenSearch, ClickHouse, Postgres, Oracle, whatever. And it's going to, on the fly, translate the queries of a specific language into another database. So essentially data migrations or just hooking up your applications to different data sources becomes much easier with this component. So in this case, what you are seeing here is actually a screenshot from OpenSearch dashboards, but the underlying data is coming not from OpenSearch, but from ClickHouse. So all those queries performed by OpenSearch dashboard are translated in the fly to SQL, and then the results are assembled so that they are compatible with what OpenSearch dashboards expects to receive. So let's have a very short look at the search request anatomy. So essentially, we post a search request to some index or some index pattern, essentially a collection of objects, similarly to a table in SQL. So we have our query block, which can have some properties, some different kinds of queries. And we also have our aggregation block. We can combine both of these, and I will be focusing solely on those two parts, so query and aggregations. Just by looking at the query itself, we can pretty much decipher what is going on. So here we are just executing a range query, and we are interested in filtering out a age property and find out those documents that match, which have this age property between 30 and 40. In the second query, we are doing pretty similar thing, except we change the age ranges, and we are performing an aggregation, which we are going to discuss further in more detail later on, which is just some aggregation. We named it total revenue from millennials. By the way, I thought that millennial is like someone in their 20s, not 30s, and I'm no longer a millennial, but apparently I am still a millennial, as I found out while making this presentation. So I'm super happy to see this. And here we have our total revenue from millennials, and we are basically calculating a sum of a order paid total field. You can essentially think of queries and its similarity to SQL language as a way to filter our data. And our query from previous slide corresponds to the following SQL query. So select every customer. So right now our customers index becomes a SQL customers table where age is between 30 and 40. We could use the between keyword in SQL, but as we go along and build more complex queries, those simpler logical conditions and actually getting rid of not introducing too many keywords is actually super helpful. So I will just rely on that. Quick disclaimer. Yes, I hope it won't break the screen share. Not sure if the screen share. Okay. Okay, good. So I want to put a short disclaimer here. For the sake of this translation between Query DSL and SQL, we are going to skip some things. First of all, we are going to skip some of the fundamental differences between OpenSearch and any kind of SQL compatible database. So in that way, obviously, the text searching capabilities are far better and far superior in OpenSearch. But we are not concerned about that. We will be just concerned about querying and the way the queries are built. However, if you're interested in those fundamental differences and the performance implication and how it works under the hood in OpenSearch. I can recommend you my presentation from this year's OpenSearch conference in Berlin, which is called Unspoken Overhead of the Inverted Index, which goes, well, not that deep, but still goes into internals of OpenSearch in a very beginner-friendly way, so that you will take a look on how OpenSearch performs way better when searching full-text data. And on the next slide, I will explain why we have to think beyond types, schema, or mappings, or whatever that is related to kind of an object. This is because if we were super meticulous about querying our data sets, types might become an issue at some point. So for instance, let's have a look at our collection of, in this example, let's look at the collection of books. We have a documents for each book, which has like an author, title, and it also may have the field of review. So in OpenSearch, we simply can check and filter for those books for which the field review exists, and we're done. However, when we enter the SQL word and SQL tables, well, if the book is just a text field, we're fine. Okay, we just select books where review is not null. If book is an array, we might need to do something like that. If reviews are some sort of map, we will have to do something like that. So our queries might slightly differ depending on the type that we are handling on the SQL's end. So I would like to give a little eye twitch and not focus too much on the types over the course of this presentation. So simple queries. Let's have a look at this one. So in this case, we are searching for customers whose name is matching the Slav. So they are Slavic. So in this case, for SQL, it would be something like this. Select every customer where name is like SQL operator Slav. So you can spot a pattern right now that we have our query block. We have a query type followed by some properties which are specific to this query type always. And they don't have to be the same as we will look at any other examples. In this case, we are searching for products which have their category property, and we would like to see the products which has category either apparel or jewelry. In this case, we use in operator of SQL, and this would look something like that. So terms query behaves in a way like this. Select everything from products where category is either in apparel or jewelry. Prefix query, in this case, we have our addresses which have their zip code. We have our query. We use prefix type query, and the zip code prefix is going to be 90 dash something. This is, again, the SQL-like operator. Of course, the simplest query to just see all the documents in the index, match all, which doesn't take any properties. This simply corresponds to select star from customers. Now we are entering something that it's going to make stuff a little more complex. So the compound query, the way to actually join few queries and perform more complex filtering data. And by the way, I am deliberately skipping some of the irrelevant, some of the query types that are irrelevant to the translation. So in this case, for the compound queries, things like this max or boosting or constant score, this will be the query types that are basically focused on the document relevance. So as OpenSearch returns some relevance in some documents in the search results, it always tells you some kind of relevance of the search. In SQL, we simply return objects, tuples, you name them, but they just go as they are. As long as they fulfill those filtering operations, they do not have any relevance. So we are skipping those score-focused queries. And how to join queries. So we have our query operator. There's specific bool query. And we have 4 options here. Must query corresponds to logical AND operation. So in this array, we will be able to insert a set of queries that will have to be joined by logical AND. Must not is equivalent to logical not. Should is the logical or, as we'll see in the next example. And there's a very handy option, the filter query. Filter query is also like a magic hint to OpenSearch, which tells that, okay, this results of this filtering should be cached. So in case you are executing several queries subsequently, it might be very useful to rely on the filter because the next results will just appear way faster. Of course, we can have like must not, and should, for instance, in one query, and then their end result is going to be a logical AND. And we'll see that example in a minute. So in this case, what are we searching for? We are executing a Boolean query, which has like must and filter parts. So these will be joined by the AND separator, and we have only one element for each query. Here we have match and name. So we are matching for names in Slav, and we are filtering our customers by age. So there's a range operator here. So again, as you can see, this is the corresponding SQL query. Pretty much makes sense. What happens if we add more? So we have a post customer search. We have a bool query. We have our should, which corresponds to the logical or, as I've told you before. And in this should operator, we have a list of simple queries. So we have a match queries to match a name, and also a terms query to match nationality. So in this case, you see something like this. We select everything from customers, and here we have our should block translated, and filtering operation, which translate to something like this. So just to give you some tip on reading and writing query, in general, it's very helpful to recognize the query type and just know what kind of query we are dealing with. Because as you can see, some of them have your field names like very shallow in the JSON. Some of them have them as nested property. So it's always handy to just know which one is which, and the bool query, and that these parts are like set in stone and you don't get to touch them. And also, what I found quite helpful is that actually sometimes when reading complex queries, it's quite helpful to just read them like both ways, from top down to bottom up, because it sometimes makes just more sense. So let's enter the aggregation part. So we have already established that the querying applies to data filtering, and let's have a look at the aggregations API. So essentially, aggregations means adding some analytics. And just by looking at this example, before we get into the syntax, I just wanted to show you this example. So again, as I've told you, we can mix both ags and query part. We use query part to just filter out the data and have our customer age set in a specific way. And what are we computing is aggregation named total revenue from millennials, and this is going to be a sum aggregation, and we will be adding up the field named order paid total in orders document collection. So when translating that to SQL, this would be something like this: select sum from order paid total as total revenue from millennials, where customer age is between 28 and 43. So now we have an idea of how the syntax looks like. Basically, we have ags, aggregation name, aggregation type, followed by some sort of aggregation properties. My tip is to, especially when we get to bigger queries, name your aggregations wisely, because sometimes it's very easy to just get lost on what is being computed, and we will see some examples over the course of this presentation, but in general, it's very useful to just name your aggregations in some sort of meaningful way. I don't want to get into the sampler aggregation, but just for you so that you know, sampler aggregation is basically an aggregation that takes only specific numbers of documents per shard. And as you noticed here, you can also nest aggregation. So you can perform an aggregation over aggregation result. There are three kinds of aggregation that are possible. So the simplest one is a metric aggregation. They perform simple calculation. End result is usually either a metric or a set of metrics. So for instance, something like average value, the sum, the maximum value, those which return like multiple metrics would be percentiles. If you execute a percentiles aggregation, it will by default output like 7 percentiles, like 19th, 95th, 99th, 50th, I think, I'm not sure, but like several of those metrics. And typically when aggregations are nested, you are going to see the metric aggregations like at the very leaf node, so to speak. This is usually going to be the very last aggregation in the nesting situation. There are also bucket aggregations, which tend to categorize the set of documents into buckets. So for instance, we can group events by day, group people by country they are coming from, and have this set of buckets of documents generated. Third, and like the most complex type of aggregation is a pipeline aggregation. In case you would like to do some more complex analytics, like cumulative sum or count derivative, you would have to pipe the result of one aggregation into another. So in that way, pipeline aggregations are quite complex, but in many cases, quite useful as well. So for the metric aggregation, so the simplest one, you can see that there's a decent set of aggregations you can perform, like average, cardinality, geobounds, which is related specifically to the geotypes, of course, sum, top hits, stats, which also returns a multiple statistics around the fields. And what would be the SQL equivalent of this query? So we are interested in cardinality of countries. So let's take our millennials and see how many distinct nationalities are there in our group of people. So we have our aggregation. I name it number of countries so that it's meaningful and I'm not lost when analyzing the query. I am using the cardinality aggregation type, and the field over which I am interested in computing is going to be nationality. So again, this is joined, followed by our filter. We have our count distinct nationality in SQL language as number of countries. Similarly, we could go to the sum and we will have like a total revenue from millennials. So something that we did before. In SQL world, that just corresponds to the sum. And as you can see, more or less, this is like the distinction between querying, which is handled mostly by this part, so where clause and filtering data, and aggregation, which presents some sort of result of computation. Bucket aggregation is the second type of aggregation, and I bet that you executed bucket aggregation at least like dozens of times, because the most common bucket aggregation so far is the histogram. Whenever you are opening a OpenSearch dashboards, these bars represent a bucket aggregation of histogram, and you have your documents bundled into those bars of a specific time frames. Another very useful aggregation is called the facet aggregation. So this will show you like the top values for specific field. So let's have a look at the example of a bucket aggregation. Again, there's multiple of them. So some of them are very much related to very specific data type, like the IP range, for instance, or geotile. In this case, we are taking our orders and performing aggregation named zero, just to keep my query short. Aggregation name zero, date histogram, and it has more complex syntax because we have to pass the field, which is a timestamp. Our interval for bucketing data is going to be 30 seconds. So we could imagine that if we have like 100 of documents, within a minute, we would have, let's say, 40 documents in one bar of histogram and then 60 in another bar of histogram. Right now, we enter a little complex moment in our SQL query building because we have to do some sort of basically basic date arithmetics. So the way we are doing it at Quesma is something that, well, I'm not sure if that's the smartest way to do it, but it seems to be working pretty well. But we are essentially converting any kind of date time into timestamp, and then grouping by that timestamp divided by 30,000, ordered by specific aggregation key, which is here in the select query. So this is our way of querying the histogram. Of course, if we were to actually present the data and return very specific results, very often query DSL will have to become like multiple different select queries. It doesn't have to always be only one SQL query. And yeah, just to give you another example of a very useful aggregation, this one is called range. So we are naming it like price ranges. We are interested in taxable total price field, and we would like to bucket our data so that we have 3 output buckets. We would have a bucket in which the products are cheaper than $50, where products are between $50 and $200, and a third bucket for like expensive products, so to speak. So you can see a result here of such query. So we have our buckets, and in SQL world, this would be something like count if function with a specific condition per each bucket. So I don't want to get deep into pipeline aggregations because these tend to be really complex, but just to give you idea of what is possible. What we are interested here is that we would like to figure out which category of product has the largest revenue, so to speak. In that way, we are performing two aggregations. So we have our aggregation that breaks down the orders into categories. We have our aggregation that is simply summing up the sales per each category. And the pipeline aggregation here is called max sales bucket. And the aggregation type is max bucket. And this is the part in which we are declaring the way that two aggregations are piped into each other. So we are piping the my categories into total sales summary. Now, this syntax can also get a little more complex, and there's lots of possibilities you can do with it. And pipeline aggregations are like subject on its own, and I highly encourage you to just look more at it, because it would take twice the time of this presentation to really get deep into it. And when it comes to translating that to SQL query, how many of you are actually familiar with the SQL window functions? Yeah, so I wasn't before I started really working on this subject as well. So I won't get too much into this query and the way it's constructed. In this situation, I can guarantee you it works. But I have prepared like a slide just to give you an overview on what window functions are and how they are helpful in these cases. So this is like a 101 SQL window function. So window functions are basically performing some calculations across a set of table rows that are always related to current row, but they still preserve the individual rows in the result. So there are two concepts here. There's a window, which is like a subset of rows in the result set, and there's over clause, which defines what is being done over specific window while iterating over a table. So just two examples of very simple window functions. In this case, we have our data for employees. They work in specific departments and they have their own monthly salaries. If we were to rank them by salary, but within a department, we would have to prepare something like this. We generate our rank, which becomes a row number, which is our window function, and over is a SQL clause, which is followed by partition by department, order by salary in a descending order as rank. This is just an alias. But you can see that our partition by department, order by salary becomes this window for which we are sliding the data and just computing results while keeping our table data here. And another small example to in case this one wasn't clear, let's have a look at the employees which have their salaries, and let's just compute the running total. So like salaries summed while iterating over employees. Like here we have 1,000, here we have 900, so we have 1,900 here. We add up the 1,100 to this result. In this case, our window function becomes the sum of salary, but this is going to be performed over hire date, which is like order by, because we need some sort of ordering closure in the window function, as running total, which essentially it is running total from employees. In case you're interested more in SQL window function, and I know this has been really aggressive and like super quick introduction to it, there is a very handy on the page learnsql.com. There's a very handy cheat sheet which will get you started really fast with SQL window functions. So I would recommend checking that out. And once you have that basics, on our blog, there is a very detailed explanation. So if you go to quesma.com, there's a blog. There's a very detailed explanations on how we are actually translating those. So I wasn't really getting into details of that pipeline aggregation query, because once you have your window functions really like down, you will be able to really get into how these translations work, and it's quite interesting. We call this pancake SQL pattern because all of these aggregations are kind of like, you know, layers of pancakes stuffed one on another. And yeah, just a good read. So I really encourage you to do it. And in case you would like to get really like super deep, even if you're not satisfied already with the how the Query DSL to SQL translation works, Quesma is actually open source. We've open sourced, I think, like 3 months ago or something. So you can see how there are, you know, unit tests, there's code, which you can see the way we are parsing queries and generating those SQL responses. So yeah, feel free to check it out. Feel free to give us a star on GitHub. It always helps. And yeah, so just to sum it up, it's been a lot of knowledge here. So we've done a crash course on Query DSL. I hope we have some framework established on how we are building our queries. We've built some understanding on how OpenSearch queries are built, and more or less what kind of possibilities are there in this realm. And additionally, there was also a little bonus on the SQL window functions, which are like super useful. Once you really get a good understanding of window functions in SQL, you will really love it, and is going to be super handy in your any kind of analytical work when you will have to deal with relational databases or analytical ones. Yeah, merci beaucoup for the presentation. That's it.
Questions? May I ask to close the Google Meet?
Yes, sure. Of course.
Thank you. Thank you for the talk. It was very interesting. So I had an idea, like, do you think it would be possible to somehow fine-tune an LLM to convert SQL queries into Query DSL? And do you think it would be, in any case, somehow precise, or it would still need work?
Yeah.
Like, how difficult would be, you think,
Yeah.
to optimize?
It's not that difficult. We did that. The
Okay.
problem, but it was for our testing purposes. The problem here is that what you really need is like a pragmatic, like a programmatic and very systematic way to translate it. So in our use case, asking LLM would just take too much time. Like what Quesma is doing is that we are translating those Query DSLs into SQL and vice versa, and assembling the response. For that, there's no LLM. There's no space for LLM, purely because of how much time does it take to just translate one query into another, and also the results tend to be very unreliable in many cases. So we couldn't do that. We did some test runs just for our curiosity and see how it works. We weren't really satisfied with that. And also, we weren't able to generate such a translation algorithm for us with LLM too. So we're not there yet with AI, apparently. So we have to code it ourselves. But yeah, purely in our case, so again, we are doing translating on the fly. So we don't want to add any kind of additional overhead or latency or anything. So just as fast as we can, we just wrote some bunch of Go code, which parses the query, translates it, and returns the results. And that tends to work best.
Okay, so for now, what you do now is kind of rule-based, basically. I mean, like LLM is generative, but what you do is like you basically have a bunch of rules, so it's rule-based.
Yeah,
and you're using rules that are dictated by the human.
Yes, yes. We've built a whole parser for the Query DSL. We have built the whole AST for the SQL, to which we are like constructing the query side by side, and yeah, that's how it works. So with LLM, what we did is that we used it for just generating some test data and having some sort of benchmark on how well we are doing. But it was surprisingly disappointing in this specific case.
Okay. Okay, thank you.
Sure.
Other questions? I had a few questions.
Sure.
So Quesma takes SQL as an input and translates it to Query DSL for Elastic, or the other way around?
The other way. So you have imagine a case where you have your OpenSearch dashboards hooked into the OpenSearch, and you would additionally like to see some of the ClickHouse or Postgres tables as OpenSearch indices. In that way, you put Quesma in front of your OpenSearch dashboards, which speaks the Query DSL over HTTP, and then you simply execute your queries as they were. We translate them to SQL, get back the result rows, and then also assemble the OpenSearch compatible response in HTTP response.
Okay, yeah. I imagine it's much slower though, no? Or
It depends. It's actually for many cases. So for text searches, it's going to be way slower. But for any kind of analytical queries, especially those numerical based, or even those like term based, so to speak, these are going to be way faster than OpenSearch. Because actually, in this case, if you choose ClickHouse for your analytical workloads, you will have like a order of magnitude faster results, just because ClickHouse uses the not row but run based in compression, so that it's just way faster to just get this all chunked data at once.
Great, that's clear.
How are you exposing the ClickHouse tables to be understood by OpenSearch dashboards? Through a connection, index
Sure.
pattern?
So in this case, oh, I should have. I'm a little surprised. I could have I could have prepared a Quesma demo for you here, but I don't have it right now. So currently, we have this abstraction that a ClickHouse table is an index, or it can be a data stream in OpenSearch. That doesn't really matter at that point, but that's the basic building blocks. So for instance, you have also the mappings API, which gets translated with specific types, which are compatible or sometimes aren't compatible. But the main level of abstraction, so to speak, is that. Just to maybe show you some, that's actually going to be a sneak peek into the configuration. Yeah, so just so that you have an example, if when you are configuring Quesma, you basically tell that you want to have your Kibana sample data e-commerce index, which data source which is targeted at is data will be coming from ClickHouse, and you can also like override some fields, specify some more advanced types. But the main idea for the abstraction is that what you want, so that you provide like what you want to present as OpenSearch index. So that's the main bridge between those two worlds. So ClickHouse tables becomes OpenSearch index.
Just a small remark. I think that on the slide with the prefix of zip code, in the SQL part, you should put zip code instead of name. Yeah, zip code like.
Of course. Gotcha. Yeah. That's nice. Anyone spotted anything else? Wow. Cool.
Otherwise, in my understanding, your Query DSL is useful when SQL cannot, or things that SQL cannot do.
Sorry, could you say it again?
Your Query DSL is useful for things that SQL cannot do, like aggregating with some of derivatives or things like this.
Yeah.
So that's the motivation for using this.
Yeah. So of course, SQL will never be superior with full text search queries, and the way to go is just to Query DSL, and it's perfect for that. However, if we take a look at OpenSearch dashboards and take a look at majority of the analytical workload that happens there, most of the time, when we perform any kind of aggregations, either bucketed or metrics, these are the cases where actually so columnar type databases are way faster than OpenSearch, way faster. Plus, they are cheaper as well because they tend to use way less storage. For instance, you don't have to build inverted indexes for all of the fields, or like half of them, or how many you would like to have. So in that way, they can be faster and more economical. If you would like to dig into that, there's a ClickHouse. I think it's this, actually, this post. Yeah. Go check it out. It's very interesting. It basically explains the cases where there are specific types of calculations and specific types of computations, so to speak, where you can have not only faster search results, but also save on storage because of the compression that columnar type databases are using. So, of course, ClickHouse will never excel with full text search, but there are still some spaces where it can drastically improve performance and cut costs. So in that way, the reason for which we are presenting Database Gateway is that you can actually have two data sources connected and just, use your favorite OpenSearch dashboards. Great interface to your data. All these visualizations, dashboards, you can still use it, but you can keep different kinds of data behind the Database Gateway and just use whatever one serves the purpose the best, and it's cheaper, or whatever the motivation is.
And are there equivalents in Python?
Equivalent in Python?
In Python, yes. Like in Python, you can do SQL with pandas, more or less.
I'm not sure if not sure if
I mean, are there libraries in Python which have the same functionalities?
Oh, you mean database gateways that are written in Python?
I'm asking you.
So to my knowledge, there is no such a solution as database gateway right now on the market. There are dozens of projects that do some kind of database translation. Like there was this project which done that similar translation, which was called Ketchup. I know that Uber did some migrations from Kibana dashboards to Grafana, I think, but mostly these solutions are catered towards specific database engine and specific technology. So Quesma is relatively young. We only support OpenSearch in the front and ClickHouse and OpenSearch in the backend, but we are planning to actually add more. So we also support hydraulics, and we have like a trial support for Postgres, and we are working on it. But we are going to develop this solution further. This is just our MVP and what we have at this moment. So yes, there are plenty of similar solutions that do translations, but again, mostly these have been like catered towards very specific technology, and that's it. Because the nature of the whole translation and connecting to different data sources is just so complex that neither of the organizations wanted to generalize this whole idea and make any kind of universal tool for it, unfortunately, or fortunately for us.
Thank you.
Sure.
Other questions? No? Speaking about the power of Query DSL and SQL, you mentioned also the and versus or queries, the should and must. And actually with should, you have like minimum should match.
Yes.
Where you have like a should, which is kind of it's not exactly or.
Yes.
If the minimum should match is not one.
Yeah, I think I also have this somewhere here. Yeah. Yes, that's a fair point. Let me add it to my notes.
So in this case, the should clause in the Query DSL is not exactly a logical or.
Yes, yes, that's very accurate. Sure. Thank you.